Yeah, the first thing has to do with the competition. And the reason to talk about it is because it's coming up very soon. Usually these ACM programming competitions are scheduled in fall, but because of COVID, things have been pushed and pushed, and now they're scheduled for March. So March 5th is the big day, and it happens here in PG6, which means that we have to look respectable, and I'm looking to you guys to put up as many teams as possible so that we can at least have a respectable showing. Yeah? So that leaves us with something like 7 weeks to prepare, and 7 weeks means 7 Saturdays and Sundays for us to prepare. I'm hoping that it's still early in the semester, so maybe you guys can put in some time and give this a good shot. Yeah. In order for that to happen, you need to register at the ICPC. Most of you did that last year, but some of you may be new, and you may want to look into registering there. Once you've registered, we will talk over here to form teams, and then I will register the teams for you. Okay. Our goal is to make the best teams possible. Well, we'll talk about that in a few minutes. Okay. All right. Then you can also go and look at old competitions from that website there. Now, well, I was hoping a bunch of new people might be here, so this is really for them. We have sessions on Tuesday, Wednesday, Thursday, and Friday. My algorithmic sessions are on Thursday. You want to tell us about the other sessions?
Yeah. So on Tuesday, David is going to go over the beginner lectures as normal.
Okay, great.
Wednesday, Joseph.
So what is the focus of the beginners, just so that it's recorded and people can watch this?
So basically we're going over basic concepts, easier problems that people might be...
Is it more programming focused or is it more problem solving focused?
It's data structure.
It's, okay, all right.
The reason why we use certain data structures.
Okay, so it's not really programming focused, it's more,
We're not
all right.
teaching them to code, we teach them to solve
Okay.
problems.
Okay, so it's still problem solving except that it's for beginners.
Yeah.
Okay, great. Then Tuesday,
Wednesday.
sorry, Wednesday, yeah.
Yeah, so Wednesday I'll be going over some of the problems that like I've gotten on technical interviews. So
Okay.
On the level of a technical interview.
Okay, all right.
And then
Much of that comes from lead code or something like this?
Yeah,
Okay,
exactly.
all right, okay, good, yeah. So Thursday is meant for us for the meeting over here. We go over algorithmic approaches, and overall, we want to learn at the level of being able to compete in competitions. Okay, and we'll talk about what we'll cover here, and then Fridays. Fridays, what happens?
Yeah. So on Friday, last time we used to review what you went over, but this time we'll take a different approach. It will be a brief highlight of what was discussed, but now we're going to actually dive into the code, and whatever Dr. Giri told us, whatever algorithm or problem we were solving with you, we're actually going to program it up in a mock competition, and we might try some other problems as well.
Okay. So what you may want to do in the first week or two is how do you solve simple problems? How do you upload it onto the onto those VJudge websites and start to compete?
So
Okay.
tomorrow specifically, we're going to be setting everyone up how to read input and output, or how to answer questions just in case, because it is different from lead code. You just have to read your input, so we're going to walk through that to make sure everyone's on the same page.
Okay. Super. Yeah. Okay. So that's the deal for the training sessions. Then, in order to prepare for the competitions, there's a whole bunch of things that we have at our disposal. The first is a North America qualifier. This is actually organized by people outside of FIU, and on the 22nd they have actual competition. And this is meant for us to figure out what are the strengths and weaknesses of different people here so that we can form teams. So I'm going to use your performance there in order to figure out how best to form teams. I think that competition is just going to be individual. You can go and check this. But this is more for our purposes to get better organized and to build better teams, okay? And it may be a good idea for you to try and get as many people for this competition, because then maybe they'll get excited and say, okay, I'll give it a try, right? And we want to form more teams of even beginners just to get a sense of just to get them trained for next year and get them excited about next year, okay? All right. So this North America qualifier is important. That's on again, I assume it's a Saturday, right? Is it a Saturday? Yeah, it is a Saturday, and it goes from 2 to 7 p.m. You need to register for that, and the registration deadline is coming up. Yeah, Ricky.
So this qualifier, like we're automatically accepted to the regionals?
No, it has no connection to the regionals. It's just more to prepare.
Okay.
Yeah. As far as I know, it has nothing to do with whether you qualify for the regionals or not. I know it's called a qualifier, but I don't think it's really qualifying you for anything. So the contest will be on Catis. Catis is just like We Judge. It's a similar thing, but it's slightly better organized. We Judge is kind of all over the place. It's a conglomerate of various virtual judging sites. Catis is just one of them. So Catis is actually included within We Judge, which you guys are somewhat more familiar with. But Catis is the one who's going to organize this contest. And there's more information here. So even your question, you should go and check over here, okay? Then besides the qualifier, Catis and the folks at USF and UCF and so on, they're organizing a whole bunch of practice sessions. So every Saturday and Sunday from now until whatever, end of February, there are mock competitions. So it's more or less like what we do, except that they have organized them, and these are problems that are closer to what you would expect in the competition. So it's probably a good idea. So this thing starts only on the 29th, so it's a week after the qualifier. And so and I think, I am not sure if these two problem sets are the same, the ones for Saturday and Sunday, but at least one of those days you guys should go and give it a shot and get to learn what kind of problems you might expect. So whole bunch of practice sessions, a real qualifier type competition, and then getting ready for March 5th. This is sort of our plan for the next 7 weeks. So if you have any weekend plans, you may want to rethink this.
Someone watching the live stream said, are the competitions age restricted?
Age restricted, yeah. So there are, I'll get to that in a couple minutes. Okay, let's talk about that actually. So before I go there are tons of repositories. Catis is one. We Judge is actually a collection of a whole bunch of other repositories. And the old one was the UVA, the University of Valladolid, which started things off, and then from there a whole bunch of other repositories followed. You can go to any of these. Essentially, you have an endless store of problems to work on. There is no shortage of problems. The only issue is that they're not well organized. You can't say, I want to go look for a problem on minimum spanning trees and hope to find one easily. That doesn't work out. And it sort of makes sense because no problem is, for most problems, there may be more than one way to solve a problem. So it's hard to hard to decide beforehand. If you want dynamic programming problems, it's hard to go and find one, but there are hundreds, maybe even thousands. Okay. All right. So teams. For the competition, they're all 3-person teams. If there are people who work together well, those could be teams. But what I prefer to do is to take our pool of talent and figure out how best to field good teams for us. Because it's really important that you complement each other's skills. One person might be good with geometry, another person might be good with combinatorics, another person might be really fast programmer, and you really want these diverse skills to come together, especially for our top 2 or 3 teams, right? So I would say maybe you can provide me with information and I will help you form the teams. That would be my suggestion, right? Okay. There is eligibility, and here's a website where you can go and check whether you're eligible or not. Hey.
Good morning.
Yep. Hey, good afternoon. So the teams are also valuable because once you form the team, it's a good idea to get to know each other, get to know each other's strengths and weaknesses, your styles of programming, the common mistakes you make, things of that sort. So we will have a team formed by end of this month, soon after the qualifier. And all of February, what I'd like you to do is to stick with your team and practice with your team. Okay? That's our plan. And yeah, it's definitely a good idea to go and check whether you're eligible or not. If you're an undergraduate, most likely you'd be eligible. The good thing is that even some graduate students might be eligible. So if you know some good graduate students, make sure you convince them to come and participate with us.
I'll look into it.
Yeah, talk to your friends.
I think I do know some good graduate students.
Sorry?
I do know some good graduate students.
Okay, yeah, send them over. So besides kind of learning from each other, one of the biggest things that happen, and you guys have experience with this, you're going to end up with bugs, and your brain is frozen, and you can't see your own stupid mistakes. Give it to somebody else to help you, your teammate. And that's where teamwork becomes very important. And even in real life, you work for whatever, Google, Amazon, whatever it is you're going to work for, you will be working in teams. These skills become useful, okay? So definitely think about this and start to strengthen your team. Yeah.
So the qualifier that's the 22nd, that's going to be individual though,
I
right?
think so. Can one of you check this, please, if you don't mind? I'll share the link again. Yeah, this is the link.
Which one is it?
There's,
Thank you.
yeah. Well, you can go to the info here. Yeah, so but what exactly were you going to ask after that? The qualifier most likely is an individual one.
Oh, yeah.
Even if it's not, it's completely okay to go and field it like an individual, just so that you get a sense, so that I get a sense of what your strengths are. Okay, that would be my suggestion, but I can check on it and get back to you as well. Okay.
Pretty much anything.
Yeah. All right.
Says here for register for the 2021-22 NAQ.
Yeah.
We will use your registration information to create teams on Katniss. So from that, I'm guessing it's teams.
But it's online, right? I mean,
Yeah,
so
it is online, yeah.
since it's online, go and work from home. You all have your own computer, so it really doesn't matter. It's equivalent to working individually. If there are virtual teams, who cares? Ultimately, keep track of what you've done and what your strengths are, and convey that to me, because that'll help me to form better teams. Okay? Does that make sense? All right, then here's one more thing that you need to know. This is for the March 5th competition. Many of you are already familiar with this. Every team, well, you're a team of three persons, 3 students, but you have access to only one machine, which means only one person is coding or debugging. The other 2 are hopefully thinking about the next problem to figure out, to solve. And you don't have any electronic media other than the desktop that you have access to, which is not connected to the internet. There are no cell phones, there are no other devices. But each team can bring a folder of stuff, and it's a good idea to start collecting things that you want as soon as possible. What exactly can you take with you yourself? Of course, since it cannot be electronic, it has to be something on paper. You can print out whatever the heck you want, that you think is important. We'll figure out a set of standard problems and algorithms, and those things you should just have ready-made code that you can just type as and when you need them. Okay? Now, it's not enough just to have code for the algorithms you want to solve. You also want to have tried it at least once, because otherwise you have no idea whether it's going to run or not, what kind of input it needs, what kind of format it needs, how do you run it. You better have comfort with those aspects. These folders, so you can print out a couple hundred pages quite easily. You can even take a book, as long as it fits within this. Okay? So there's a thin competition algorithms book. I'd be happy to share that with you. I have 2 or 3 copies, but you're welcome to go and purchase them. They're maybe $15, $20 or so. So as long as it fits here, and the width of the folder is 2 inches at most. This is 12 inches dimensions. As long as you're within those dimensions, you can take whatever you want that's not electronic. Okay. You can print out things from the web. You can print out programs you have written for yourself that you've tested out. Do whatever you like. Start to collect them now. Okay. There are books to help you prepare, and here I have mentioned 4. This one is online, so you can go and see what's useful from there and print out whatever you want from there. Okay. Remember, you have 1 folder per team, so it's not 1 folder per person, it's 1 folder per team. And these other books are quite useful as well. I have copies of all of them. I'll make them available to you. You still have keys to the lab there, and I'll keep all the books on the shelf outside. You guys can go in and look at them, share, study, or if you can find PDF like many students do, power be to you. Yeah. So overall, this is the date we want to target for. That's our immediate goal. Okay. For some of you, this may not be a priority. I still would love for you to participate and help us field good teams. That's the plan. You don't have to be an expert programmer. If you even enjoy the spirit of competition and the spirit of problem solving, go and enjoy the day. You don't have to be competitive. You can go there just for enjoyment if you wish. But of course, as I said, my goal is to make us look respectable, right? So I want us to train for that for the next 7 weeks. After that, we can decide how we're going to take the rest of the semester. Okay? And going back to the topics. So these are the topics that that show up in every competition. And most of them are familiar to you. Yes,
Yeah.
sir.
What's familiar to me is like the graph two algorithms, like the district and DFS, as well as the first review of graph theory.
Yeah, I'm getting to it. Yeah. So what I've identified 5 kind of major topics. First one is I put dynamic programming, which is in my opinion the first non-trivial set of problems show up there. And there are the dynamic programming problems kind of get progressively harder. I can make them hard enough that I wouldn't know how to solve. So these are, and they always show up. There's always dynamic programming problems, sometimes even more than one. There are always some math problems, permutations, combinations, counting. Then there are a bunch of other things, and things that depend on permutations and combinations like exhaustive search. So that's another group of problems. So exhaustive search, some of those problems may come from graph theory, may come from number theory, may come from something else. We just don't know. Okay? So there's overlap between some of these areas, but this is more to get what the basic ideas are. Then we have graph algorithms and tree algorithms, and as he mentioned, there's depth first search, breadth first search, minimum spanning tree, shortest paths, all pair shortest path, topological sort. And then there are tree algorithms like tree traversal and various tree processing algorithms. And then there are advanced graph algorithms, which almost always show up, but these are typically quite hard. Unless you have mastered this, there's not that much point in worrying about this. Okay? These have to do with connectivity, various stronger versions of connectivity, and network flow. Network flow is a very, very important topic, but usually it's much more advanced and requires fairly sophisticated thinking. It's unclear if we are quite ready for it, because we need to get through all of this and be comfortable with them before we can get there. But again, each of you is at a different level. Feel free to find your comfort level and start to attack these problems. Okay? And finally, we have these miscellaneous problems. There are geometric problems, both in just plain geometry versus geometric algorithms. Then you have string algorithms. And even within strings, you have combination type things as well as string algorithms. Then a whole bunch of number theory algorithms, prime numbers, this, that, sums of numbers, partitions of numbers. There's just a gazillion problems there. These are all, they infrequently show up. There's almost always at least one geometry-related problem, but what kind is hard to guess. So that's roughly where things are. It's very hard for everybody to be master of everything. Pick your comfort area and focus and try and get some expertise there. Once you form your team, see if you can divide the work a little bit so that you say, all right, all graph problems, you're going to take care of it, okay? So that you first attack it, see if you can solve it, and if necessary, get the help of your teammates. That's going to be the approach that we take. Does that make sense? And almost every competition has one or two very, very simple problems. And even though they are simple, the focus is on speed. So there's one other aspect of all of this, and that is, even for simple problems, how fast can you type and get the darn thing to work? And that's a different skill that doesn't look like your regular problem solving skill. Some of that is how fast you type, some of that is how fast you debug, and some of that is how fast you can get it to compile and run. And that's a skill that one of your teammates needs to have, because as people get off the gate, within roughly 3 minutes, somebody has solved one problem. And if you wonder how the heck anybody can read a problem, code it up, get it to work, well, you'd be surprised. Maybe, and you guys can get there as well. And so part of the training is also, let's take some easy problems and figure out how fast we can do this. All right? So that's another thing that you can do on Saturdays. You can do some speed tests where it's like a 100-meter sprint, and you say, okay, here's a new problem, very simple, absolutely nothing to really think about, but you got to code this and get it to work, and give it to each of yourselves, and let the clock run, and see how fast you can do this, because that's a good training to have. And all of these are useful problem-solving skills. It's not just for the competition, and we've talked about this before. You guys are sponsored by Google, so they look for skills of this sort. And now, ever since Google has done this, the other companies have followed, and so there's now a whole slew of these companies that want the same skills. As the interview season starts, all these skills are going to be useful for you. So 7 weeks of hard training can't go waste. That's the way I look at it.
Even if the company's trying to recruit you like Apple.
Can you repeat that,
Even
please?
if the company's like, even if the company's trying to recruit you like Apple, like you're like kind of nervous to do that interview. You want to make sure you nail it the first time. That means you have to get a guaranteed job.
Yeah. Yeah. Well, a lot of this is about building your own confidence. If you feel comfortable and confident, then these challenges can be handled. If you convince yourself that you're never going to be that good, your prediction might end up coming true. So you have to push yourself, and this is just like physical training, just like training for football or athletics or running. You can train yourself to be good, and that's ultimately what it's all about, and that's what we're trying to do. Unfortunately, I'm not really training people at the lowest level. I just want to devote the next 7 weeks for people who've been at our training sessions before and who want to compete at the highest level. Okay. So don't count yourself out. Feel free to be here and think with us and work with us. That's what I'd say. Are you with me? Yes? Very good, very good. So that's all for that's all I have to say about the competitions. And the only reason to bring it up is because it's really coming up now. Any questions, any comments, any thoughts on our plan? So in terms of the topics, I need some feedback from you guys, because I can pick almost any topic and spend time. For instance, if I picked one of the advanced algorithms and talked about network flow, I could easily spend 2 weeks just explaining to you how to do this, and we'd burn away two good weeks, and maybe you'll be able to attack one problem, and it wouldn't be clear if you can solve it or not. So it becomes a crapshoot. On the other hand, some of these other things, especially dynamic programming, for instance, I think you can be trained to solve the problems that show up there. So I could give you some of my suggestions, but I'm happy to listen to what the thoughts you have in terms of where you want to go.
Yeah, I think over the past year, we focused on graph and tree algorithms.
Yeah.
That's a lot of the recordings that are already in the YouTube channel.
Sure.
So I think we should not focus on that.
Not
Maybe
focus on the graph and tree.
Not focus on those, but still put them into like the competition. So if we have any issues.
Well, the
go back to-
competition, since you're going to do the qualifier and the other things, you're going to see them anyways.
Yeah,
So,
like the Saturday. stuff.
right. Oh, our Saturday stuff for the next 2 weeks. Sure. Yeah.
Maybe some stuff we haven't really done is geometric algorithms and
Yeah.
some combinatorics. Those two topics, I would recommend focusing on.
Okay. Geometric algorithms and combinatorics. Okay. Other thoughts?
To be fair, I'm leaning towards doing classical graph algorithms because I'm more familiar with it. But at the same time, I'm geometric algorithms. I'm not that familiar with it when it comes to the coding part, but
Yeah.
at the same time, I'm actually familiar with it because in a mathematical sense.
Yeah. But as you heard him say, there are lots of recordings that you can go and listen to
Yeah.
on graph algorithms. So there's a good way to catch up on graphs.
Yeah, which I can
And I think I've done quite a detailed one on all these ones, the depth first search, breadth first search, minimum spanning tree. And I also have, that same Saturday, I've given you problems related to them. So, there's a way to train for those if you talk to one of the other team members here. But geometric algorithms I have not done in the past. Geometric algorithms have not been a favorite with you guys.
That was the first one you gave us.
I'm more than happy to go back to it. In fact, that's I spent maybe 10 years of my life doing research on geometric algorithms. I'm happy to go back and talk about this anytime, any day. You can wake me up from my sleep and I'd probably start talking about this. So I think those two are good choices.
I was gonna say, what's your opinion on us covering math problems?
Yeah, so the combinatorics, permutations, and combinations would come under the math problems.
Okay, yeah.
They almost always show up, at least one. Often they are in conjunction with dynamic programming, because a lot of the combination problems you end up solving using dynamic programming. But none of these problems are totally disjoint anyways.
No.
You need skills from all over the place. It seems like you just have to be smart all round.
Also, I might be being a little greedy, just for my personal interest, but
Uh-huh.
centroid decomposition, the tree centroid,
Yeah.
that might be a good topic. To
Okay.
Find contour and trees. A little advanced, but it seems
It's not that advanced, so yeah, I think we actually solved one problem with that. In fact, if we can find that recording, maybe that's something we could share. I think you may have missed that lecture.
Why are you recording? What's your recording?
I can give it to you guys.
Yeah. Yeah, and this goes for everyone who's listening to this tape recording. Make sure you find out where all the YouTube channel where all our past recordings are, and you'd find a wealth of stuff. This is one of the reasons why I asked you to put the topics there, because now it'll become useful for people to go back and look for this, right?
The thumbnail also has the topics too, so if you guys are just looking at the screenshot, you can read the thumbnail.
Yeah.
But someone on the live stream says that dynamic programming, they would feel, I know we've done it before.
Yeah, would be nice to cover that. For sure, I'll spend a little time on that. So dynamic programming, geometric algorithms, and combinations and permutations. Okay, sounds good. Some of these are pretty hard, but we'll definitely go and look at these. Other thoughts? What you will also find is that there are many problems from other areas, maybe from graphs, maybe from trees, which if you think about it deeply enough, you'll see that it ends up being a problem on combinations, for instance, or something else. Or there may be something that doesn't look like any of these, but suddenly you model this and it looks like a graph problem or a dynamic programming problem. that's a skill that we only acquire by looking at more and more of these examples. And that's one of the things that we will focus on here. Yeah. What I'm trying to say is modeling the problem so that it looks like something you know how to solve. Modeling the problem like a minimum spanning tree problem. Modeling the problem so that it looks like an exhaustive search problem. These are all skills that we will acquire over time. Okay. And one thing for you, David, if you're talking to other graduate students, there are many of them who've been in competitions before. See if any of them are interested in just joining our teams. So if they have prior experience, then it becomes a lot easier. Then we don't have to explain to them. Then they may not need a specific training, but we could put put one graduate student in each team, and we'd be quite awesome.
I'm in the Iyengar class, AI in forensics.
Yeah.
Forensics.
Yeah.
There's like 10 students in there.
Uh-huh.
at least. I could ask them.
Yeah, so typically, I think if you look at the eligibility, only the first and second year graduate students work out. The senior PhD students, you can forget it. They would never qualify.
There's a lot of private.
Yeah, so yeah, definitely. I will also ask some, but you may have access to other students. And some of you may be taking senior classes where there are some graduate students. So
They do not qualify the senior PhD.
Senior PhD.
They're overqualified?
No, I think there's some age required. There is an age requirement. Well, let's take a look. I can't even remember anymore.
Yeah, if you're born in 1986, you're eligible.
What?
Yeah.
That's
If not, you have to go down the tree.
Let me do it.
Check off a couple of things.
All right, where is this
Epic
now?
balls.
Oh, here, yeah.
No, it's
Yeah,
not.
sorry.
Okay, so what's the first condition? 1996?
That's one later on. This is a pretty long tree.
Okay.
Yeah, the first one is.
Let's put it up here.
Yeah.
Because this is kind of critical, isn't it?
Yeah.
Okay, so, all right, the first one says willing and able. Okay, that's not a problem. Enrolled in degree programs, so that's not a problem. Taking at least half a load, so you can't be a part-time student just taking one class a semester. Competes for only one institution. As long as you're not trying to compete from two different institutions, you're okay. Foreign student visa, well, what is it? Does permit return from, so if you're just visiting here from Colombia or something like this, then there may be some issues, okay? What is this? Number of finals. Can you read that? Oh, number of finals as contestant. So how many of you have been on how many, if you've been on more than what? More than two.
Finals.
Oh, I'm sorry, guys.
That's too good.
Well, we've only been on regionals. None of us have ever been on finals, so that's not a problem.
Yeah.
If you've been on more than 5 regionals, then it's a problem. I don't think any of you have been with me for more than 5 years, so that's not an issue. And then basic requirements. All right, year first began post-secondary studies, 2015. What is post-secondary? I assume that's after high school?
Yeah, oh, it's after high school?
Yeah. But if you come from other countries, then there may be slightly different standards, and you may have to kind of think hard about this. Then born after 1996, completed more than equivalent of 8 semesters of full-time STEM study, whatever the heck that means. So this is where some of the graduate students become eligible.
There's someone in the live stream that I think he's dependent on your petition. Because he was.
So we can petition. Yeah, we've petitioned in the past.
Okay.
And
I sent him your email so you can.
Sure. Yeah. Just ask them to get in. Yeah, get in touch with me, guys. If you think you're borderline and you're not so sure, I can get things verified early on and make sure that you're eligible. Okay. How about you, David? Are you going to clear all the conditions?
Calculations right now. Well, I've done 8 semesters, but these masters, they're doing 2 at a time, so it's not full-time semesters. So, I mean,
It's a little gray area. So,
not full-time.
8 semesters of STEM study.
Yeah.
There you could kind of argue that you didn't declare computer science until,
Oh, yeah.
I don't know, something later. So those are all things you could use.
More than, so 8 is good. More than.
Equivalent of 8. Actually, this is, right now, this will be 9.
We may have to petition you to make sure that you're okay, but it shouldn't be a problem. I think we should be able to get through. So anyways, it's not straightforward for all of you, but for most of you it should be. Any questions? All right. Sorry? Yeah. Well, they want to make sure that it doesn't degenerate into a bunch of PhD students competing with each other. That's all. Yeah. Yeah, I'm going to talk to, there are 1 or 2 professors who are algorithms experts, and if they have PhD students that they have trained, hey, maybe we could just get them and have them take care of network flow or something like this. All right. We are at 4:15, it seems. No, what time is it? 4:30. We have about 50, well, I usually stop at 4:45. I have a problem that I have some slides for a problem that I've done before, that I've solved before, but maybe there are enough new phases that we could quickly go over this. Okay. This one is called fix the pond. I don't know if you remember this problem. You do. Okay. Yeah. So you guys can take a little nap. How many of you have not seen this problem? Okay. 1, 2, 3, 4. Okay. So at least 3 or 4. Okay. Good. So I'll give you a minute to read this. Are you able to read it? You want the website?
Oh, yeah, actually, that was.
Here. That's what you want?
Yeah. Well,
UVA 12529.
Wait, so is it the graph diagram? Like, I know that, yeah. It is against the graph, though. I can see it. What kind of graph, though?
So the challenge is in modeling the problem correctly, and then it just becomes very, very easy. Otherwise, if you try and solve it as a combinatorial problem, then it's essentially unsolvable. Okay. So can someone take a shot at explaining the problem for the others? Yeah, go for it.
Basically, yes, shrimp. You want the shrimp to go through the whole pond, but the way
Not the shrimp, I think it's the cleaner, right?
Oh yeah, the cleaner is going through the shrimp pond.
Through the shrimp pond, yeah. Uh-huh.
And he wants to clean everything.
Right.
But he has to start from one place, and that's the top left corner.
Right.
And he wants to explore the whole pond.
Right.
However, the way they set it up, you cannot do the whole pond because there are walls. There are rotating walls.
Yeah. And
such
the
that-
walls can rotate around these points.
Yeah.
Hold on. Yeah.
And what did you say something?
No.
No, I'm not saying anything. I'm trying to
Hold on.
figure it out.
Hold on. Yeah.
Okay. So you want to find the minimum amount of rotation you need, such that now the cleaner can go through all the tiles and all the spaces in the pond. to
Right.
Clean the whole thing.
So if you look at this picture, you see that you start here and you go around and you get to this point. So essentially there are parts of the pond that don't get cleaned. However, if you flip some of these, so for instance this guy here can be flipped at the center and suddenly it becomes vertical. Okay, this guy here, which is horizontal, can also become vertical. This vertical one can become horizontal. So if you make the changes that are shown here, then suddenly the cleaner can go through all of this and finish up.
Yeah, I just remember this bomb because it basically.
Hold on. Let's get these guys up to speed. You're a little bit ahead of the game. I'll ask you in a few minutes. So the question is, which of these switches do I have to flip in order to cover the whole pond, in order to clean the whole pond? Is the problem clear? Yeah? Okay. And every piece of wall is only, it only spans 2 of these cells. Okay, each one is only 2. And for every piece of the wall, there's a little center around which you can rotate this. Yeah? So the question is, how many of these do I have to rotate and flip in order to ensure that the whole pond can be cleaned? Now, there are lots of these, and if you try combinatorial approach, you could say, let me try flipping every one and try every possible horizontal or vertical configuration of those flips, and one of these should work, right? The only problem is there are too many of them. There are too many combinations. And the question is, how do I figure out which one? Yes, sir. Now tell us
Basically,
what you remember.
how you figure it out is basically by actually, I would say like, judging by the flow the stream is going, as well as the direction the stream is going, you have to literally just go through it via by direct, you go through it via by direction. That means like, you can't go back to the certain place. You can't go back to certain place. So you gotta keep going in the direction that's easy straight. But you flip switches in case you see an overflow or to understand a connection.
Uh-huh.
So in this case, the reason why we're flipping is because not only that you're supposed to keep going straight, you're supposed to keep going like in the direction you're going through. So to actually get to the next area, it is flips, which is okay, but I I already know, but I just don't know how to explain it well.
Okay, all right. So let me try and write down the problem a little bit more in more detail. So the barriers, each of these is a barrier. Okay, there are lots of barriers. The barriers, each barrier can either be in horizontal or in vertical position. If it's in horizontal position, it sits like this. If it's in vertical position, it'll sit like this. Okay, because you flip it at the center. You can see that over here. This is vertical. In this picture, it's horizontal. It's exactly at the same position. So what we are interested in is where are all these centers? And you see that in each row, every alternate position is a center of a barrier, right? Is that clear?
Yeah, that's clear.
Okay. And there are 2n plus 1 rows. There are 2n rows and 2n plus 1 columns. If you leave out the first row and the last row, on every other one, there are alternate positions where the barriers can flip. So how many total number of barriers are there? Right. So, if you take 2n by 2n plus 1, every row has n of these barriers. And there are how many different rows?
There's six, there's six
It's
rows, for example.
2n minus 1, isn't it?
Yes.
Wait, for rows?
No, it's 2n rows and 2n columns.
Oh, but the number of barriers is
So n barriers per row, right?
yeah.
And how many rows?
2n rows.
Well, there are 2n rows, but the first row doesn't count,
Yeah.
right? So it's 2n minus 1 multiplied by 2n minus 1. This is the number of barriers. Did I get this right? Yeah? Each barrier, you can either put it in horizontal position or in vertical position. So think of that as 0 and 1. So it's a binary state, right? Each barrier is either horizontal or vertical. Is in H or V state. Are we clear about this? And now we want to know if we can find the position, the state of each of the barriers, we would know exactly how many we need to flip. Right? The only problem is that there are almost n squared barriers, right? And so there are 2 to the n squared different combinations that you would have to search, because each one can either be 0 or 1, horizontal or vertical, right?
Yes.
That's too many. And if n can be as big as what? It's on the next slide.
Obviously, with n being bigger,
N can be as big as 300. You're in deep trouble if you're going to try every possible combination, because 2 to the power 300 is a heck of a lot.
yeah, that's 90,000. That's 90,000. 90,000.
2 to the 30 is something you can handle. That's roughly 1 billion. Anything more than that, you're in deep trouble.
90,000 and 1 billion. That's like a lot right there.
So we're not going to try every possible combination. That's the first thing you need to rule out while you go through the thinking process for this. So that means we have to think about this problem in a very different way, right? And it turns out that there is a simple way to think about this. And by the way, the input is given in this manner that tells you on each row there are 3 barriers. This tells you the first barrier is horizontal, the second one is vertical, the third is horizontal, and so on. This is the same as the example on the previous slide. So the first one is horizontal, horizontal, and then 3 verticals. You can check here. Horizontal, horizontal, and then 3 verticals. Right? So it's the rest of it is exactly this picture. So you're given this picture and you want to know how many you need to flip in order to create a scenario where the cleaner can clean the whole pond. Is the problem clear to you guys, the ones who have not seen this before? Are you okay with this? You need to slow me down and ask me questions because these guys have seen it before. Don't listen to them.
Oh, so I got a question. So the ones that are switching are those ones are kind of the scenario, or are those the ones that we need to flip?
Are those the ones what?
Kind of as one as a scenario, or those are the ones that we need to flip?
You're given this scenario. The input is given over here. This is the scenario you're dealing with.
Okay.
From this scenario, you want to know how many I need to flip.
Okay.
Okay?
Which is in turn watching the what?
So this that input turns out to be exactly this.
Oh, okay.
Okay? And you want to know how many I need to flip here, the minimum number that I need to flip here in order to be able to go clean up the whole pond.
Yes, okay. Now I understand what you're doing. Okay, thank you.
Yeah.
Thank you, okay? Thank you.
The middle point of the barriers is always alternates
Yes,
between.
that's correct. Yeah, it always alternates. That way you can turn them without hitting each other as well.
And that there won't be no fixed solution. There should be just like multiple solutions to this one.
You because you're only asked for a number, you don't care if there are multiple solutions. You just need to provide the minimum number. So the minimum number is going to be whatever, an integer.
Yeah.
Right? So there's only one answer.
Oh, okay.
If this is the input that's given to you, then you're going to answer 0 because nothing needs to be flipped.
Yeah.
If this is the one that's given to you, you know that it can be done with 1, 2, 3, 4, 5, and 6. By flipping 6 of these barriers, you know that you can achieve the solution. The question is that the best possible? Can you do it with less?
I think yes.
Someone's asking to clarify what you mean by flip.
Flip. Okay, so as I said, if you look over here in this example, this barrier, let's look at this barrier here. Okay, this barrier has a center over here. In this configuration, it's vertical. In this configuration, it's been flipped and it's now horizontal. So that's a flip. So every barrier can be flipped on its center. You can either go horizontal or vertical. If it's vertical and it's flipped, it becomes horizontal. If it's horizontal and it's flipped, it becomes vertical. That's it. These are the only 2 states. Is that clear?
Let's do another one.
If they were all horizontal, then you get the whole one.
No.
If all of them
If they're all horizontal, then you will definitely make it. Yes, that's correct. But there may be other ways to do it too. That's the problem. So if you make everything horizontal, that would mean 1, 2, 3, 4, 5, 6 flips, which is the same as that. But it turns out that you don't have to make everything horizontal, and you can still make it to work. So how does one figure that out? But you're right, if everything is horizontal, that would work, because then you would have space over in this corner, and yeah, you would go zigzag, right? Yeah. Right. Any thoughts from this end of the room?
I'm thinking it's like there has to be a pattern.
There has to be a pattern.
Yeah, like a condition where like a certain horizontal barrier can't be adjacent to like a vertical barrier. That's the only thing.
Yeah. Well, all right. So let me show you a few slides, and then maybe you can think again. So first of all, it always starts from that end and always finishes at this end. And first of all, every configuration, regardless of whether you put them in horizontal or vertical, you can always get there from here. That's something, if you stare at it, you'll see is true. Doesn't matter how you set them up, you can always get from the blue star to the green star. Okay? And that actually you can even prove mathematically, but we won't get there for now. Now, here's the next observation. There are a bunch of observations that we're going to use. Okay? Yeah, so let's, we know that the barrier centers are at these red dots. You can see the red dots, right? Yeah. Yeah? Yeah, it's meant to hypnotize you. So at that red dot, your barrier, which is shown in yellow, can either be vertical or horizontal. Now, here is the deal. If I look at the cell next to one of these barriers, that's colored in yellow there, then depending on whether it's vertical or horizontal, the neighbor of that cell is going to be different. So if it's vertical, then A and C are neighbors, B and D are neighbors, meaning you can get from A to C and from B to D. If it's horizontal, on the other hand, then you can get from A to B and from C to D. Okay? Is that clear? Okay, so I've drawn a little squiggle there for you to see. If it's vertical, because the barrier is not horizontal, you can now go from A to C, right? Now, this happens at every barrier, all right? Which means that if I, what is it? What am I trying to say now? I forgot. So now if I just look at two adjacent barriers, it'll tell you exactly how the path is going to go. Because for any cell, let's look at this particular cell that's colored in yellow, it only has two neighbors. Because if this is vertical, then this neighbor and this neighbor are going to be locked out, because both of these are vertical, which means it only has two neighbors above and below. If both of these were horizontal, it would only have neighbors along that row. Or if one were horizontal and one were vertical, it would have one neighbor this way and one neighbor that way. So every cell, regardless of the configuration of the barriers, will always have two neighbors. That's it. Okay?
D will also have a neighbor, C will also have a neighbor, and D will also have a neighbor. It will also have a neighbor. And horizontal or vertical directions.
Yeah, hold on. So if every cell has only two neighbors, which means you can only go to two of the neighboring cells, then what does that tell you?
There's certain combinations of barriers where they might isolate they might isolate cells.
All right, so now I want you to think, now I want you to forget about cells. Now I want you to think about vertices in a graph. Let's imagine that each cell is a vertex in a graph. Okay, and every cell only has two neighbors. What does the graph look like? So I throw in a bunch of vertices, all right? Doesn't matter what they look like. And every vertex only has two neighbors. Hold on a second. Now, two neighbors means, what is it going to look like? From here, I can only go to two of the neighbors. Let's say this and this. From here, one neighbor is already counted. I can go to only one other neighbor. So if I'm coming in from one, I can only go to one other neighbor, right? I don't know. Let's say that one. That guy already has one neighbor counted. I can go to only one other neighbor.
And now we get the GDSC algorithm.
Now what?
Now we get the GDSC algorithm.
No. Don't jump yet. You're not there yet. You're not there yet. What does the graph look like? You're not answering the question.
Oh, okay. All right.
Sorry? Connected. Well,
A networking graph?
not quite. Forget directed. There are no directions. I haven't put any arrows there. It's not directed. Components. What do you mean components?
There's different components in the graph.
So you're saying exactly the opposite of what he says. He said connected. You're saying not connected but components. Okay.
Well, there's going to be one. So it's going to be disconnected sub graph.
Okay, but what are each of those pieces going to look like?
They're all going to be, can I just, cycles. They're all going to be cycles, but one's going to be an actual.
That's right. So if every vertex only has two neighbors, then everything eventually must come back to the same vertex.
The one vertex.
No, you're jumping way too much. Hold on. So this can have only one other neighbor here. This can have only one other neighbor. This can have only one other neighbor. And maybe that other neighbor is over here. Once I connect these, none of these vertices can connect to anything else because they all have two neighbors. Right? So now what do I do with the rest? So in a graph, if every vertex has two neighbors, what does the graph look like? Forget buzzwords. Tell me in plain English, what does that mean? Sorry? Cycle. Very good. So it's going to be a collection of cycles. However, there's one major hurdle. If you go and look at the vertex way up on top left, come on, yeah. If you go and look at the one way up on top left, that guy doesn't follow these properties. It does not have two neighbors, it has only one neighbor. Same thing with the bottom left, the destination vertex. It has only one neighbor, regardless of how you put. So if you put this as vertical, this has only one neighbor. If you put this as horizontal, it has only one neighbor. So there are two special vertices that have only one neighbor. Everything else has two neighbors. So now how do we change your statement? What does the graph look like? And this goes back to what David was trying to say. And anyone remember what David was trying to say?
It's a bunch of subgraphs.
Bunch of
Components.
bunch of,
Vertices?
bunch of, bunch of cycles. Thank you. So there are going to be a bunch of cycles, but one of the components is not going to be a cycle because it has two vertices that have degree 1. If you have degree 1, you cannot form a cycle. That's not possible. Okay? So now the graph looks over here. One piece is going to just look like that because there are two vertices that have only degree 1. Everything else has degree 2. This is an example of a graph where there are exactly two vertices with degree 1 and everything else has degree 2. Is that clear? So if you have this kind of a graph, it'll have one path and whole bunch of cycles. This is a graph where there are exactly two vertices with degree 1 and all other vertices have degree 2. Is that clear? Now, if we want to be able to have the cleaner clean the pond, what does the graph need to look like?
Just one path.
Just one path, no cycles. Okay? So you want to go from here to a single path. Now, when you flip one gate, what happens? Over here, the reason I cannot visit the whole thing is because there are cycles here, right? Here's one cycle, here's another cycle, here's another cycle, and here's another cycle. There are 4 cycles. So how do I visit the whole thing? Very simple. If I flip one barrier, what happens? Let's say I flip this guy here. It's horizontal, I flip it to vertical. What do you think will happen? Or maybe it's easier to see a different one. Let's say we pick this guy here. If I flip that vertical to horizontal, what do you think will happen? It won't disconnect. What is it going to disconnect? Go ahead.
Oh, I was going to say it doesn't connect to the...
Look, right now, this here is just a cycle, right? And the path goes around it. If this were horizontal, what will happen?
Like it'll connect that cycle with that.
Right. So from here, you'll go like that, and you'll go on. So therefore, it's going to essentially eat up the cycle. Right? So when you eat up the cycle, you're now reducing the number of cycles by 1. So by flipping this guy, I reduced it by 1. On the other hand, there are going to be some flips which will actually increase the number of cycles by 1. And you have to watch out. So all I have to do is to count the number of cycles here. For each cycle, one flip will incorporate that cycle into the path. And the number of cycles will be the minimum number of flips that I need to get it to work. So here, I will flip that guy first. Then in order to take this guy, I'll take this one and flip this way. What will happen? It will incorporate this cycle, right? In order to incorporate this cycle, I'll take this guy and flip it this way. And then finally, to incorporate this cycle, I have to just flip this or this. It doesn't matter which one. Does that make sense? So 4 flips and I'm done. I don't need 6. Is that clear? So you take this structure, build a graph, count the number of cycles, and that's your answer. All right, I have to stop here. Gotta go.
Thank you, Giri.
And so counting the number of cycles, how long does it take? What's the time complexity? It's basically a graph problem, right? And you've done this before. Each cycle is a separate connected component. You might as well just count the number of connected components. You can do that with depth first search. That's linear time. So in linear time, you can solve this problem as opposed to the combinatorial approach, which takes you 2 to the power 300. Yeah, okay, thank you.
I want you to take it from here.
Appreciate that.
Yeah, done it? I tried it. I attempted it.
Thank you, Giri.
You're welcome, sir.
I literally was like, I don't know why, but I was like, literally like, okay, I know what this is, but I don't remember what the word is.
Yeah, that's completely all right. You don't have to worry about that. It's very hard to go through these, yeah.
Like the fact that like I was like, wait, this is like a connectivity problem, and I was like.